You have your computer?
Yes.
Perfect.
So, thank you. Well, I'm going to present myself first. Houssam KANSO. I'm a researcher at the LIUPPA, the Computer Science Lab of the Université de Pau et de Pays de la Dour, and this paper entitled Automated Power Modeling for Computing Devices, Implementation and Use Case for Raspberry Pi. It's quite a long title. Was published in the Swisscom Journal and co-authored with Adel, Noureddine, and Ernesto Exposito. So to start with the introduction, I will point to two things that my previous colleagues, the two previous presentations already said. Chantal said that it's quite difficult to measure. And Gael said, we saw that if we don't measure, we don't know what is really happening. So the first step towards reducing the energy consumption, in my opinion, is first to be able to quantify how much energy each device is consuming. So this is quite difficult because we don't always have access to these devices. So sometimes devices are not accessible physically. And another challenge will be that these devices are heterogeneous. Even if two devices can accomplish the same tasks, a lot of times they can consume different power consumption. One additional challenge is that devices may change with time. So for the same device, it can have updates, software updates, its location can change. So maybe it was in a cold location, then it was in a hot location. So the environment changed, therefore maybe the power consumption will change with it. And finally, the solution that already exists are either difficult to implement or specific to one or to one type of devices. Therefore, just to see a little bit of the existing solutions. So some existing solutions are based on hardware power measurements. So we just plug a watt meter and like this, we know how much the device is consuming. Yes, it is accurate. It's the most accurate way to know how much the device is consuming. It is adaptable because if we change the device that is connected to this watt meter, it's going to give us the new power consumption. However, it's time consuming to connect each of the devices to these watt meters. It's cost inefficient because if we want to buy watt meters, it's going to cost us. We need physical access to the devices in order to plug them, and it doesn't scale. Well, the other solution is to use software power estimations. So software power estimations are less accurate than hardware ones. They are not adaptable. So if we create one for a specific device and then we want to apply it to another device, maybe it's not going to be accurate. It's less time consuming. It's not as costly as a hardware solution. We don't need physical access all the time to the devices. However, they lack when it comes also to scalability. So what we are proposing is to try a little bit to take the advantage of each of these solutions. So what we propose is an architecture where we have three types of devices. A power meter. It's a physical power meter, but I'm going to explain about it a little bit later. So the three types of devices that we have are data collection and benchmarking clients. We will have a power modeling server and a power estimation client. So the idea here, the goal of this research is to generate power estimation models for connected devices. So if we want to look at it from a different way, we have data collection and benchmarking clients that are connected to watt meters. They share their metrics with a server that we call the power modeling server. And this power modeling server is going to be based on the metrics collected from the devices, and the data, the power collected from the power meter is going to generate power estimation devices that are going to be used later by the power estimation clients that are clients that don't have watt meters connected to them, but that they may have the same type of data collection and benchmarking clients. So if we take a deeper look at the data collection and benchmarking client, we have a few components in it. First, we have the power collector that collects the power consumption from the watt meter, the physical watt meter. We also have the metrics collector that collects data from the software and the hardware of the device. So it collects information about the device and it collects information about the software. For instance, for example, how much CPU are we using? These two information are then sent to the sharing interface that is going to share both this information with the modeling server. So if we take also a closer look at the power modeling server, we're going to see that it collects this information, it's going to synchronize, clean data, and all this. And then it's going to model, to use this data in order to generate a power estimation model and then to validate it. And then it's going to do this not only based on the data that is collected right now, but also on the historical data and from different devices that are contributing to this power model. So for our experimental setup, we tested this on some raspberries, the raspberries that we could get. So ranging from the Raspberry Pi 0W 1 until the Raspberry Pi 4. So first, we prepared our raspberries with the scripts, and we applied some interference reduction protocol. So mainly in this study, we were based only on the CPU cycles. So what we did is that we stressed the CPU from 0 to 100%, and then we collected the information from the CPU cycles and the power, and then we mapped, we generated the power estimation models. Then we shared them with the server where the models were generated, and we have generated linear and polynomial regression. We're using linear and polynomial regression because there is a high correlation between the CPU utilization and the power consumption. So for our results, we have generated models for all the devices that, or the raspberries that we saw in the previous slides. We have calculated the error rates of these power estimation models. For instance, they are ranging for the linear ones from 0.34 to 7.8, and for the polynomial ones from 0.3 to 3.8%. Then we have calculated the difference in the overhead between the linear and the polynomial to see do we prefer using polynomial or linear? And we found that the difference was really small. So the idea is with each iteration, we want to improve our model. So we have also tested this. So we have launched the experiments on different devices from the same type that are sharing the information. And each time we receive new information, we check if we want to generate a new power estimation model or not, in order to gather as much as information as we can in order to generate more accurate models in order to converge at the end. We have also tested the impact of revisions. So the impact of revisions between raspberries was not, they didn't have a lot of impact. However, the number of bits had a lot of impact. So if we use a Raspberry Pi with 64 bits, a model generated for this Raspberry Pi on a Raspberry Pi with 32 bits is going to give erroneous data, erroneous results. We have also tested connecting peripherals. So we have connected some USB wired keyboard, activated the Wi-Fi, the Bluetooth, and we found that that the way we generated the model still was acceptable. However, it gets higher if we use a model that was generated for a Raspberry without these peripherals on a Raspberry with these peripherals. Finally, we compared our approach to two approaches that already exist. So the problem with approaches that already exist is that Okay, they make the experiment, they publish a paper, and then for one device, and that's it. So what we propose here is to like collaborate all devices together in order to keep generating these models. I think I don't have a lot of time left. So I'm going to jump directly here. We have tested it also on a, not only on a Raspberry, we made a small experiment on a smart lamp. So taking the state, the color, and the brightness, and we found that with different colors, we had different power consumption, maybe because the lights that are being turned on in order to make the new colors are so we turn on more lights to make new colors other than red, green, and blue. And finally, for future work, our perspective is to cover additional hardware components, study more machine learning algorithms, because if you want to add more metrics and more metrics, linear and polynomial regression maybe are not going to be the optimal way to generate power estimation models. We want to study external factors and cover more devices. So to sum up, we have it's important to quantify the power consumption of different devices. Here we created, validated, and shared power estimation devices across various devices. And these are my references, and thank you.
Thank you very much.